So let's start with a little bit of a review. Let's say we got a submarine here with a 3-foot glass window in it, and it's 200 feet below the water in a lake. Why don't you find the force on the window? Okay, so why don't you pause the recording and then see if you can do that, and then we'll go over it. So I'm going to pause here. Why don't you pause and see if you can get that number, and then once you've got the force on the window, just start the recording up again and we'll go over it. So we've got the window is a 3-foot diameter, and the window is the center of the window is 200 feet below the surface of the water. Okay, so see if you can pause the recording and then see if you can figure that out. All right, hopefully you've been able to knock that one out. Let's see what we got. So let's start this thing up and see what we got. Okay, so what we're going to have on this one is the pressure would be the 200-foot depth times 0.433 psi per foot. That would be 86.6 psi. So to find the force on the round window, what we would do then would be to find the radius of the window, which is 1.5 feet, and importantly we want to convert that into inches. Okay, 12 inches to a foot, that would be an 18-inch radius on the window. We want that in inches because we have PSI over here, pounds per square inch. Okay, then we want to find pi r squared for the window. That's 1,018 square inches. Multiply that by the pressure, and we'll get 88,159 pounds on the window. All right, so when we look at the area of that window in square inches, it's quite large, and with the depth there we get quite a lot of pressure, so those two things together get a very large force on the window. Let's look at some other aspects of force here. First thing is transmitting force with a hydraulic jack. So with a hydraulic jack, what we have here is a piston that pushes on a container of hydraulic fluid. Okay, so we're going to push, in this case with 100 pounds, down on that piston. That piston will push against the hydraulic fluid in here and will cause pressure to build up in it. Now what's going to happen with that pressure is it will act everywhere in the fluid. On the other side, we've got a larger piston. That pressure will push against the larger piston and push that piston up and exert a force. So what we'd like to know here is if we've got a 1-inch radius piston on the left and a 3-inch radius piston on the right, and we push down with 100 pounds, how much force up will we get? Okay. Now this is a little different than what we've been doing here so far, because what we're going to look at now is the pressure in that hydraulic jack that's caused by the 100-pound push on the piston. We're not really looking at elevation change for pressure on this. We're just looking at the pressure caused by the 100-pound push of the piston. Okay, so what we would want to do would be to find the pressure on the left where the 100 pounds is exerted. We could find the area of the piston. That would be pi r squared. Okay, so pi times 1 inch squared would get us 3.14 inches squared. We know we're pushing down with 100 pounds, so if we divide that by the area, we'll get the pressure in the hydraulic fluid. It's 31.8 pounds per inch squared. Okay, so what we're using there is the idea that pressure is force over area. Now what we can do here on the other side is use the idea that force is pressure times area. So we find the area of this piston with a 3-inch radius. It's 28.27 square inches. Multiply that by that internal hydraulic fluid pressure, and we'll get 900 pounds. So what's happening here is if we push down with 100 pounds on the left, what we end up with is 900 pounds on the right, which is, a pretty good thing here for a hydraulic jack. Now, of course, what you lose on this is distance. If you want to lift something with this jack, let's say a car or something like that, you're going to have to push this little piston down a long way to get much movement at all out of the piston on the right-hand side, okay? So a lot of distance on the left will get you a little bit of distance on the right. So small force, large distance on the left gets you a large force and a small distance on the right. Okay. Now, there is a shortcut on this if you have round pistons, because what you're doing there is you're going to start with the pressure on the left, which is F1 over the area, which would be pi R1 squared. That's the pressure, and then multiply that by the area on the right, which is pi R2 squared. Okay. Now the pi's will cancel, and what you end up with is F2 is F1 times R2 over R1 squared. So this is a shortcut method for a hydraulic jack problem. So you can just take 100 pounds times 3 over 1 quantity squared. That would be 100 pounds times 3 squared, which is 9. 100 times 9 gets you 900 pounds. So that's a quick way to do that. Okay. So that's one application of force. It's a little different than what we've been doing here so far. Another application of force is called buoyancy force, and that's the force that allows boats to float. Okay, so that boat might well be made out of steel or something like that, which of course is quite heavy, but if you shape it so it's hollow, you can have it float. All right. Now the idea of buoyancy is if you submerge something, there's an upward force created called the buoyancy force. The upward force is equal to the weight of the fluid, which in our case is water, the weight of the water displaced, which is moved out of the way by the object. So if you take this block and submerge it, there's going to be an upward force on it equal to the weight of the water that is moved out of the way by the object. So if you find the volume of the object and multiply it by 62.4 pounds per cubic foot, you'll get the upward force of buoyancy exerted on the object. Okay, and then you can compare that to the weight. Okay, and if the buoyancy force is greater than the weight, the object will float. If it's less than the weight, the object will sink. Okay. All right, so let's have a look at this next one. Let's say we've got a sluice gate there, 2 feet by 2 feet by 4 inches. And the gate weighs 39.39 pounds. Let's find the net force on the gate. Okay. So what we would want to do would be to first, so that's 2 feet by 2 feet by 4 inches, which is 0.333 feet. Find the volume, which would be 2 feet times 2 feet times 1/3 of a foot, which is the 4 inches. So we want to get everything in feet so the units match here. And so the volume of that rectangular gate would be the 3 dimensions multiplied together, 2 by 2 by 0.333. So that's 1.33 cubic feet. We know water, and it's on the formula sheet there, weighs 62.4 pounds per cubic foot. Multiply that by the volume, you get 83.2 pounds. That's pushing up. Okay, so we've got that upward buoyancy force. You have the weight, and to get the net force, you'd want to find the difference. So we've got an upward force of 63.2 pounds, a downward force equal to the weight, 66.39. So the difference is an upward force of 16.8 pounds. So if you take that gate and put it under water, you'll have a net upward force of 16.8 pounds. All right, so that's about it for this session here. We'll finish up force next time on Wednesday.